Welcome to Real Learning Center. So today we're going to basically start a new topic on gravitation, and we are going to cover basically four important sessions. We are going to have four important sessions in this. The first one we talk about Newton's universal law of gravitation, and then we talk about in the second one how acceleration due to gravity g varies. How does it vary? Is it constant or does it vary? In the third one, we talk about the Kepler's laws, which actually talks about elliptical orbits and etc. And finally, we talk about the potential energy, kinetic energy of the orbits, and also orbital velocity and escape velocity. How do we go away from Earth? Okay, these are the points that we are going to talk about. Now, let's start with the first one, which is what we call universal law of gravitation. So, before we actually get into the universal law of gravitation, we are going to basically ask a few questions, and these questions are actually quite important because that will create a certain understanding at the you start basically thinking about those. Okay, so the questions are here. And the first question is: Earth attracts people, rather not just people. Earth actually attracts Apple. Due to gravitational force, as we saw, Newton saw that the apple dropping and he talked about gravitational force. Earth attracts apple due to gravitational force. Does apple attract Earth? That is the question. Apple is falling towards Earth. Is Earth falling towards apple? Interesting question though. Okay. So the next question is, if you actually drop apple, okay, it falls to Earth. That you know. Anything you can drop, it falls to Earth. But the question basically is that if you actually say that the gravitation is responsible for apple to fall to Earth, and at the same time it is also the moon which is basically going around the Earth because of the gravitation, then why isn't the moon falling to Earth? Earth is attracting this moon. Why isn't it falling to Earth? So that question next begs an answer. Okay. So the next question is, if all objects attract each other, okay, according to Newton's law, Newton's gravitational law, every object which has mass attracts every other object. If that is the real case, then let's say I keep two books on my table, and those books have to attract each other, and gradually will they move towards each other, let's say even slowly for hundreds of years, will they come to join each other? That is the question. Okay. Now, finally there is one other interesting question somebody asked me. If you actually drill a hole in Earth, and hypothetically, don't say I can't drill a hole, okay? Hypothetically you drill a hole so that it reaches the other side of the Earth, okay, and you have a full hole from one side of the Earth to the other side. Now if I drop a ball into that, what will happen to that ball? That is the question. Okay. Interesting question, think about it. After we finish our gravitational understanding, so we should be able to answer these questions. Then we know that we know gravitation. Okay. So now let's look at basically the most important of all is the Newton's universal law of gravitation. Okay. Universal law of gravitation. What is it? Let's see. Let's say two masses are there. Okay, mass m1 and mass m2. So you can write 2 kgs, 5 kgs, whatever. Okay. Now I am going to basically say that they are separated by a distance r. Let's say 10 meters, 5 meters r. So please make sure that you understand how I am measuring the distance. I am not measuring distance from the end of one to the beginning of the other. I am measuring from the center to center. Okay. So distances have to be measured from center to center. That is the first learning. Okay. Now when you do that, and then Newton says that these two actually naturally attract each other. They may not be magnets, they are just masses, anything, it may be a stone, but they attract each other with a force F. That means M1 attracts M2 with a force F, and M2 attracts M1 with the same force F. So same force F acts on both of them. So what is the value of this force? That is what basically Newton tells in his law. How much is this force? So he says the force is actually proportional to the product of the masses. What does it mean? It means actually if you take mass 1, let us say it is 2 kgs, and you double it, make it 4 kgs, then force also doubles. Okay, one of the masses if you double, force doubles. The other mass also if you double, then what happens? Force will become 4 times. So that means force is getting multiplied. Now the masses are getting multiplied to get the force. That is written as F is proportional to m1 and F is proportional to m2 together. So product of those masses. And one more thing that is realized by Newton was that if you actually take the masses and bring them nearby, okay, instead of 10 meters you bring it near to 5 meters. So when you bring it near to 5 meters, then you realize that you actually reduce the mass, distance by half, by a factor of 2. That means it becomes half. Okay. So then gravitational force increases. Okay. Gravitational force becomes 4 times. You reduce the distance by half, gravitation becomes 4 times. So you increase the distance by 2. That means if you double the distance, then gravitational force reduces by 1/4 times. So this is basically some kind of a squarish way it is working. So he says that force is actually inversely proportional to r square. R is nothing but distance between them. So it is directly proportional to the product of the masses and inversely proportional to r square. When such a scenario comes in maths, we generally write it as, we can combine them. We say m1, m2 in the numerator and r square is actually in the denominator. So F actually is proportional to m1, m2 divided by r square. Now when there is a proportionality sign, we can always replace the proportionality sign with a equal to and a constant. So we can write F is equal to g into m1, m2 by r square, where g is a general constant. Okay, this constant is actually known as gravitational constant. It's a universal constant. Wherever you go, it's the same constant. It's called a gravitational constant. So this basically what we call as the universal law of gravitation. Why is it universal law? Because it is applicable everywhere in the universe. Anywhere you go in the universe, on any star, wherever you go, 2 masses if you keep, they attract by this force. So that is what Newton discovered. It's called Newton's universal law of gravitation. Now, let's actually look at it, the way it plays out. So let's say I am standing in free space outside the sun, outside the earth. This is our mother earth and we are standing I am standing in space. Now when I am standing in space, okay, let us say I have with me 2 things. There is a person with space suit standing there, and there is one huge rock here, where you can see. So they are separated by, let us say, some distance, 10 meters r. Really what happens is that each of them actually have force on each other because of the Newton's law of gravitation. So you can say there is force F on each of them, and that force pulls them because there is nothing to stop them. So pulling them towards each other, you can see that they are coming towards each other. As they come towards each other, it is increasing the speed and finally they will come to close to each other. Okay. So you can see that actually the rock traveled slightly lesser distance and the astronaut traveled slightly higher distance. Though the force on each one of them was actually equal. So forces are equal, but accelerations on each one of them are different. Okay. So why so? It's acceleration really, because it is force, speed is increasing, so we call it acceleration. Okay. Acceleration on each one of them will be different. Why so? So it is because of another law of Newton, which said that acceleration is equal to force by mass. This is Newton's second law. So he says that the masses are different. The rock has higher mass and the astronaut has lower mass. So acceleration is equal to force by mass. Though forces are same, since denominator reduces means acceleration increases. Denominator increases, acceleration decreases. So that is the reason when you actually have 2 objects, one bigger, one smaller, or one higher mass, one smaller mass, when they are there, they may have same forces acting on them, but they may move differently depending on their masses. Okay? That is what we have to understand. Now the second part, let's go, is to find out how strong is this gravitational force. How strong is it? How much is it? So to know that, we have to really calculate the gravitational force. So how do we calculate this force? So let us calculate the force on a 2 kg ball. Okay. So I have a ball which is 2 kgs. Okay. And this is kept on a table of 1 meter height. Okay. Now such a ball basically experiences gravitational force from Earth. Earth's gravitational force. How much is that force? Can we have a number to it? So we can. Because in physics, unless you calculate, it is not physics. Okay? We need to calculate. Now how do we calculate? So we have this formula, F is equal to G m1 m2 by r square that Newton gave. To calculate now, you need the value of these things. Like Earth's mass is 6 into 10 power 24 kg. That is the Earth's mass. 6 into 10 power 24 kg. And that means 6 followed by 24 zeros. That is Earth's mass. It's huge. Okay. And the ball's mass is just 2 kg. Then distance between them is 6,400 kilometers plus 1 meter. What is that? Because you have to measure the distance from center to center. Okay, so the center of the Earth means Earth's radius is 2,400, like 6,400 kilometers. Plus 1 meter above the ground is basically your table. Okay, so total that much is plus maybe a few centimeters at the center of the ball. So now if you take that as the distance between the objects, and gravitational constant is actually given by a value called 6.674 10 power minus 11. It's a very small value. Okay. So that is gravitation. It's a weak force, gravitational force. Now, if we take this and substitute into our original formula, we had this formula F is equal to G into m1 into m2 by r square. I'm going to basically keep putting these values into it. First one is F is equal to G. In the place of G, I'm going to put 6.674 into 10 power minus 11. And then in the place of M1, I will put 6 into 24, 10 power 24. And M2 is 2. Okay. So the distance between them, I'm going to write it as 6,400 kilometers. Means 6,400 followed by 3 zeros, meters. Okay. Plus 1 meter I am leaving it. Okay. That's negligible. Square. So that because r square, there is a 2 there. So if I calculate this, so you can either use calculator or calculate otherwise if you can fast, you will get 19.6 something, okay, Newton. 19.6 I will write, 19.6 newtons. Because it is force, we will use the unit newtons. So force on the 2 kg ball is 19.6 newtons. So we have calculated exact amount of force. Now, what we are going to see is that if you look at this Earth and the ball, the force on the ball we said is how much? 19.6 newtons. And we also said now ball actually pulls the Earth with the same force, which is also 19.6 newtons. Only difference is mass of the Earth is like 6 into 10 power 24 kg and the mass of the ball is just 2 kgs. Yeah. So if you want to calculate the acceleration of each one of them, acceleration is given by Newton's another law, second law, A is equal to F by M. If you want to calculate using that, then you will get A is equal to 19.6 by 2, which is nothing but 9.8 meter per second square. Okay, that is what we got by dividing by 2. 2 is the mass. Same way you divide it here, which is 6.6 into 10 power 24 kg, you put it in the denominator. 19.6 by 2 will come to 3.3 into 10 power minus 24 meter per second square. So minus 24, 10 power, which is absolutely small, very, very small. That is the acceleration of the Earth. Okay, so it's not zero. So there may be many such balls and people around the Earth. All of them are causing actually a little bit of acceleration in all directions, and they are probably neutralized. Hence, Earth doesn't move anywhere. Okay, so the ball's acceleration is given by 9.8 meter per second square. Now, that 9 point meter per second square, what we have, we call it as acceleration due to gravity, because that is an acceleration happening because of gravity, and it is always denoted by the letter small g. You can see acceleration due to gravity is small g, lowercase g. Uppercase G, capital G, is called as gravitational constant that we saw. Lowercase g is acceleration due to gravity. Okay. Now, is this acceleration due to gravity, is it different for different masses or is it same? That is the question. Okay. Now let's look at, is g constant for other objects? So what we say is basically g is constant for any object at a given height. How is that so? Instead of 2 kg ball, if I kept a 3 kg ball, so the acceleration due to gravity for it also will be 9.8. So you put a small 1 kg, 2 kg, 100 kg, 1 gram, for anything it is exactly 9.8. Why is that so? So we can figure that out using simply math. Okay, you can say we have calculated f is equal to g into m1 m2 by r square, and we substitute everything and got 19.6. So while doing so, what exactly we did, you see? Okay, the first part, that m1 is nothing but the mass of the earth, and that m2 is nothing but the mass of the ball. Okay, now if I take the, just leave the m2 part and remaining I will compute. Okay, and that computation if I do, I will get it as 9.8, and that m2 you can keep it as m2. So our f is nothing but partially calculated. 9.8 into m2 is what we got. Okay. We claim that this 9.82 is nothing but small g, that is acceleration due to gravity. So let us see, acceleration is what? F by m. Any acceleration when you want to calculate it is f by m. F is 9.8 m2 divided by m2. Okay. So when you do like that, m2 gets cancelled and you get 9.8, and we call it g. G is 9.8 meter per second square. That's what we get. So whatever the value of m2 you take, finally that m2 gets cancelled. Whether it is 2 kg, 4 kg, 10 kg, 1 gram, everything gets cancelled. Hence, you are going to get basically 9.8 only. And that 9.8 is nothing but same for any value of m2. Hence, the acceleration due to gravity is constant for any given height. This is mathematical, but it is possible to show it experimentally. This was first done by Galileo. Okay. What Galileo did was, he showed it experimentally. He one day called all the people of a place called as Pisa. In Italy there is a place, town called Pisa. He called everybody. And there is a leaning tower of Pisa. Okay. On that he stood and he dropped 2 different masses. One higher mass, one lower mass. Because people always believed that higher mass will come faster towards Earth. Lower mass will come slowly towards Earth. Because Aristotle had said it. So people had believed it. Galileo wanted to disprove it experimentally. So he just dropped them. So when he dropped them, they actually came down at the same time. So both reached the bottom together. And that 9.8 meter per second square is same for any mass. That is the conclusion. So we proved experimentally and also theoretically, that is mathematically, why 9.8 is same. So hence, acceleration due to gravity g is considered to be constant for any mass. Okay. At a certain height. So we are not changing the height here. Same height. Is it different for different heights? We'll see that later. Or is it same? It is generally accepted to be same for our practical heights on the Earth's surface. Okay, wherever you take on the first floor, ground floor, not much change. A little bit of change only. Okay, it is still considered 9.8. And it may be little different even on the Earth. Because Earth's shape is not perfectly round. Okay, so in some places it is slightly more, in some places slightly less in the second and third digit after the decimal point. But you can always take it as 9.8 for all practical Okay, so Galileo showed it experimentally. Now, the question of basically what happens when you say that moon actually rotates around the earth, but it doesn't fall. Why so? Because we say it is centripetal acceleration. So that means that it makes it rotate, go around, but never actually makes it fall directly to the earth. So such a scenario, why does it happen? So why isn't that like apple that is falling onto the earth? So you see, suppose if suppose moon is actually coming from somewhere. I mean, that's not the theory. Okay, moon actually started basically because of the explosion, some part of the earth and all that is there. But assume for now, the moon is actually coming from somewhere at a certain speed. Okay, it's coming at some constant velocity. When it comes here to the earth pulls it and it tries to fall down. But that falling makes it actually change the direction of the speed. At every instant it is trying to fall, but it already possesses certain speed, and because of that, it doesn't actually fall, it goes around. Going around is what is called as continuously falling. It is more about whenever you have an object which is already possessing a certain velocity which is perpendicular to the acceleration. If the velocity is in this direction and acceleration is in this direction, if they are perpendicular, then the acceleration is called as centripetal acceleration, and it causes a circular motion. And that circular motion sometimes is circular, sometimes is elliptical, but it is nevertheless not going to fall, it's going to go around. So that is why in most of the celestial bodies you see Earth going around the Sun. All of them is because that there is already a certain velocity possessed by the Earth, and hence it is, if Earth stops, the day Earth stops, it starts moving towards the Sun and one day fall into the Sun. If the moon stops, it will like an apple fall into Earth. Since it is not stopping, it is actually going around. Remember that. Okay. So now after having seen all these things, can we answer some questions? Earth attracts apple due to gravitational force. Does apple attract it? Yes, with the same amount of force. It is just that its acceleration is so small that it is not going to basically fall towards the apple. And we also figured out that if you drop apple, it falls to earth, and why moon doesn't fall? It goes through a centripetal acceleration. And we also talked about two books on the table. The two books on the table actually attract. There is a force between them. They can't come to each other even after many 100 years, mainly because the frictional force on the table is such that it is balancing the force and it is not allowing it to come. It can never exceed the frictional force. Gravitational force is not that strong. However, if you do the same experiment in space, they will come nearby because there is no frictional force. Okay. And last question of drilling the hole, I am not going to answer with this video. So we are going to basically go to the next session, trying to find out the variations of G. So then we will get an answer to this question. Till then, we have completed universal law of gravitation. We got a basic understanding. We're going to get into the variation of G as the next one. Come back and watch the second video. Thank you.